Okay, welcome to our fourth class, which is Data Structures 3. This is our last class in our Data Structures unit. And today we have not too much material to cover, but the material is pretty conceptually hard, so we'll probably go pretty slow. Okay, let's first start with a review of Mohs algorithm, which is what we did at the end of last class. So this is an algorithm that allows us to solve problems where we have to answer queries on subarrays and there are no updates in the problem. We do not need to be able to update the array. And this means that we can answer the queries in whatever order we want. So how Mohs algorithm works is that we will loop through the queries and we will answer them one by one. And as we loop through our queries, we will maintain some segment of the array. I call this the current segment. And also we maintain the tag. We maintain some information about the current segment, and I call this the tag of the current segment. Okay. So in the beginning, before we start looping through the queries, we initialize the current segment as the segment from index 0 to 0, so just the segment containing the element 0, and we initialize the tag accordingly. And to answer the query, we just add and remove elements from the end of the current segment until our current segment matches the query range. And as we add or remove elements from the end of the current segment, we also update the tag so that the tag always matches the current segment, okay? And then when the current segment matches the query range, we will have the tag of the queried segment because we are always updating the tag accordingly. And then we use the tag to somehow answer our query, okay? So for example, in the beginning, our current segment goes from just holds a single element 0. And then suppose our query range is something like this, or draw above. So what we will do is we will extend the current segment by adding elements to the right all the way until it reaches all the way here. And then we will remove elements from the left all the way until the left endpoint of the current segment matches the left endpoint of the queried segment. And every time we add or remove elements from the current segment, we will also update its tag, which is some like information about the current segment that changes depending on the problem. So now that our tag matches the query segment, we can use it to answer the query. And then, for example, if the next query is somewhere else, like maybe here, we will have to add elements to the left of the current segment until the left endpoints match up, and then we would delete elements from the right of the current segment until the right endpoint also matches up, and so on. And Mohs algorithm is mainly about the ordering of the queries. So it turns out that we can order the queries in some way such that the number of times we add or remove elements, or in general, the number of times that we change the current segment is O of n root n in total over all queries. Okay. So here's an example problem that we kind of briefly went over at the end of last class. So we have an array and we have a bunch of queries. Each query gives us a subarray L to R in a range A to B. And it asks us for the number of elements inside the subarray from L to R that are inside the range A to B. And there are no updates here, so we can use Mohs algorithm. And the tag is something we decide according to the problem. So the tag of the current segment for this problem is going to be a segment tree built on the occurrence array of the elements inside the current segment. Hopefully everyone is pretty familiar with like segment trees on occurrence arrays by now. So basically, if we just imagine a multi-set containing the elements inside the current segment, then the segment tree on the occurrence array is going to model that multi-set. Okay. So to add or remove elements from the end of the current segment, this is similar to adding or removing elements from a multi-set. So we can update our tag just using a segment tree operation, right? For example, if we want to add X to our multi-set, so suppose we want to add an element to the edge of our current segment and the value is x, then in our current array, we want to do something like O of x plus plus. And this is, and to update our tag to reflect this, we just need to update a single index in our segment tree. Okay, and same thing with removing. Everyone should be pretty familiar with this stuff by now. So to answer a query for the number of elements in a subarray in the range A to B, assume that our current segment matches the query segment so that we have the segment tree on the current array for the queried subarray, right? So to find the number of elements in the range A to B, we just need to query our segment tree, our tag for the sum of the range A to B. Okay, because since the current segment matches the query segment, the multi-set that our current array segment tree is like models holds exactly the elements of the query segment. So we can just query the segment tree for the range A to B. So the runtime of this is n root n log n because the current segment changes n root n times, and every time we change the current segment, we need to perform a segment tree update. Right, so we just multiply those two values together and we get n root n log n, which is pretty big. It might not work for n as 100,000, but it might work for like n as 20,000 or 30,000 or something like that. Okay. So now let's move on to, so the reason I want to go over this problem again is because today we will learn some stuff that will allow us to solve it a little bit faster. So first, let's look at a solution to this problem using segment trees. And in this segment tree, a tag of a node representing the segment L to R is going to be a sorted vector containing all the elements inside that range. Okay. So for example, if our array is like okay, sorry that my pen is acting up again. Okay, so for example, if our range is something like, I guess if our entire array is something like 5, 4, 3, 2, 1, and suppose a node in the segment tree represents this range, so 1 to 3, indices 1 to 3, then the tag of this node is going to be the vector, or in array list if you're in Java, 2, 3, 4. Okay. So before we talk about like how to build or update the segment tree, I'm curious if anyone can tell me how this can answer our queries efficiently. I'll give you guys like maybe 1 minute to think about this. Okay, so sure. So usually in our segment tree problem so far, our query function returns the tag, or eventually return the tag of the query segment, right? So in this case, if we do that, we will we will eventually receive a tag of the query segment, which in this case is going to be a sorted vector of all the elements in the query segment. So we can just use binary search on that sorted vector to find the number of elements in the range A to B. Okay. It turns out that this isn't the best way to do it, but it's a really good idea. And we will look at why this doesn't exactly work for this problem. But first, let's look at how to build our segment tree. So one way to build it is for every node, we just loop through its segment and then add those values to the vector, to the tag of that node. And then we just sort that vector. So this is the most naive way to build our segment tree. So our build function, as usual, takes in the index of the current node and also the range L to R that the node represents. So let's just loop through all the elements in our array from index L to R, and we add them to the vector add them to the tag of our current node. And then we just sort the vector, okay? So after this, we have calculated the tag of our current node. So we just recurse. If we're not at a leaf node, then we just go to its children and recursively build those two. So this will build all the nodes in the segment tree. So my question is, what is the runtime of this thing over building all nodes? Okay, good. So the answer is n log n log n, or n log squared of n. Log squared of n just means log n multiplied by log n. And the reason why, let's look at each level of the segment tree to see how much building that level costs. So segment tree looks like something like this. These are the segments that the nodes represents, and so on. So suppose let's look at any arbitrary level in our segment tree. Suppose we are looking at some level where there are let's say m nodes on that level. For example, on the third level, there will be 4 nodes. But let's look at an arbitrary level. So let's say that level has m nodes. So the length of each node's segment is going to be n over m, right? Because the nodes approximately divide the entire array evenly. Okay, so every node on this level has length n over m. So the cost to build that node, we have to loop over n over m node elements, and then we have to sort those elements. Okay. So the cost needed to build each node here is going to be n over m log n over m. Right. So the cost to build this level is just we multiply this thing by m because there are m nodes on this level. Okay. So this m and the m on the bottom in the fraction over there cancel out. So now we have n log n over m. So this is the cost needed to build this level in the segment tree. Okay. And we can change, and this is less than or equal to n log n. Because we can just get rid of this divided by m, and that will make the quantity larger. Okay. And it turns out we can't really simplify log n over m because log n over m is just log n minus log m, and the log m is like a constant, so it kind of disappears when we talk about big O. So we have n log n time to build each level of our segment tree. So since there are log n levels in total, the total runtime is going to be n log squared of n. Okay. So that's that. Okay. Let's look at a different way that we can build our segment tree. In this one, we actually try to merge tags as we usually do in the segment trees we've seen so far. And it turns out that given two sorted lists A and B, we can merge them together in the length in time proportional to the sum of their sizes. Okay. Let's look at an example of how we can do that, of how that works. So let's just create two sorted arrays. Something like that. So to merge these two sorted lists together, the algorithm is to just keep looking at the front of the two lists and just take the smaller element. Okay. And this is because this works because the smallest element that has not been taken so far is always going to be at the front of one of the two lists. So let's just run through this. So the smaller element of the two at the front so far is 1. The two elements are 1 and 2, and 1 is smaller. So we take that and put it into like our answer vector, and we remove that from A. And then we keep repeating this until both arrays are empty. So 2 is smaller out of 2 and 3. Now 3 is smaller out of 3 and 9. 5 is smaller out of 5 and 9. And now since A is empty, we only look at B and we just put the elements of B to the end. So if one of the array elements are empty, then we can just put the other array, we can just put all of its elements at the end of the answer vector. Okay. So the code for this, we aren't going to actually remove elements from the front of A and B. We would just use two variables I and j that will keep track of which index is the current like front, quote unquote, front of the vector A or the vector B. Okay. So we have a while loop. We are not done until as long as like I is less than 8 outside, which means that A is not empty, or J is less than B's size, which means B is not empty. If at least one of those are true, then that means we're not done yet. So under what condition do we take the first element of A instead of the first element of B? Well, if B is empty, right, if J is equal to B outside, then we will always take the first element of A. Otherwise, if A is non-empty, if we enter this case, we know that B is non-empty. So if A is also non-empty, and also the first element of A is smaller, then in that case, we also take the first element of A. Okay? It's a pretty long if statement, but this is all this should be all the conditions that mean we should take the first element of A. And if this condition does not hold, then otherwise we should take the first element of B. Okay. And every time we take the first element of some vector, we increment I or j appropriately to kind of model or reflect removing the first element of that vector. And at the end, we return our answer, which will contain which will be a sorted vector of the elements in both A and B. Okay. So we can see that this algorithm runs in time linear in the size of A plus the size of B, because this while loop is going to occur exactly size of A plus size of B times, right? Because every time we go through this while loop, we add exactly one element to our answer vector. And inside this while loop, everything's constant time. So the runtime is actually this, the size of A plus the size of B. Okay. So now that we have our f function that we usually use in segment trees to merge tags, we can just build our segment tree by merging tags together, right? And I guess C++ implementation details, these ampersands here mean that when you pass the vectors into the function, it does not try to make a copy of them. So that's just a C++ implement detail to make the runtime actually what we expect it to be. Okay, so now my question is, what will be the runtime using this algorithm to build the entire segment tree? Using this f function and just combining the tags of the children to get tags of parent nodes, what will be the runtime to build the entire segment tree? Okay, yeah, the answer is n log n. And here's one way to look at it, I guess. The runtime to build each node, right, is simply the length of the length of its node segment. Because suppose we want to build this node, right? To build this node, we will combine the vectors of its two children. And this would take the time equal to the sum of the lengths of the vectors of its two children, right? But the sum of those two lengths is just the length of our node segment itself. So the time needed to build each node is just the length of its segment. So that means on every level in our segment tree, right? The total time needed to build that level is just O of n, because each node takes time equal to the length of its segment. So when we add those all together, we get the entire array. For example, on this level here, every time we add up, each node takes the length of its segments, and when we add those values together, we get n, the length of the array. So on every level, the building takes O of n time. And since there's log n levels, it takes n log n time in total. Okay, this is very similar to in the first segment tree class when we were building the array just by looping through its segment. For example, when we were doing a sum segment tree, we would find the sum of every node just by looping through its segment, and this would build in n log n time. So this is the same idea where we're basically just looping through every node segment to build it. Okay. Any questions on this? So this is faster than the previous one, but the previous one is definitely easier to code. So up to you which one you guys want to use. Okay. So now let's talk about how to query our segment tree to answer a query. So suppose we want to answer the query in the form of find the number of elements in the range A to B inside the subarray from L to R. Okay. So usually what we do to answer queries with segment trees is we use our query function and we kind of merge tags together until we eventually have the tag of the query segment. So we can't do that here, and we can eventually get the tag of the query segment, which would be a sorted vector containing all the elements in the query segment. And then we use binary search to count the number of elements in the range A to B. Can anyone tell me why this might not work? I don't think why this is not like log n time. Okay, I guess this is implementation specific, but let's say we want to find the tag of the query segment, right? So over the course of our depth first search, we will begin with like, we can kind of imagine like beginning with an empty vector, and over the course of the depth first search, eventually like we merge stuff into this vector, and eventually this vector becomes the vector of the query segment, right? But suppose we query for the entire array. This means that at the end, we somehow ended up with a vector containing the entire array, right? A sorted vector containing the entire array. But this is like a new vector. So this must have taken like linear time in total, right? We somehow created this new vector because every time we merge stuff together, we kind of create a new vector, and then we add stuff into it. So you can imagine the last time we combine two tags together to get the tag of our query segment, this will take time O of n, right? For example, let's say our query segment is this, and right before we get the tag of the query segment, we're going to merge the tags of two segments, for example, like this. And this last step by itself is already going to take linear time. It's already going to take time equal to the length of the query segment, which can be O of n. Okay. In reality, it's probably even a lot more than O of n. I'm not sure, maybe high constant factor, but yeah. Maybe there are ways to implement this so that you can do it in log n time, but I don't know about that. I don't know any way to do that, at least. So instead, what we are going to do is we are going to look at the log of log n number of disjoint segments inside the query range. Right. So we have our query range here, and our segment tree query function is going to find a bunch of disjoint segments that partition the query range. And there are going to be log n of these disjoint segments. Okay. So what we can do is that for each of these disjoint segments, we have a sorted vector containing all the elements inside it, right? So for each of these disjoint segments, we use binary search to query the number of elements inside that segment in the range A to B. And if we add all these values up, we should get the number of values in the entire query subarray in the range A to B. Does that make sense? So take a moment to read this again, I guess. Yeah, so to reiterate, I guess, for this segment here, we're going to count the number of elements in the range A to B. And then in this segment, we're going to count the number of elements in the range A to B, and the same for all the other segments, okay? And if we add all of these values together, since these segments that we individually counted partition the query range, if we add all of these values together, we will get the number of elements inside the entire query subarray in the range A to B. Okay. So can anyone tell me the runtime of this method? Okay, yeah, the runtime is log n squared or log squared of n. And this is because there are going to be log n disjoint segments, right? Log n of these guys, because that's just how we talked about this on our first class. This is how symmetry works. And for each of these log n disjoint segments, we need to binary search inside its vector to count the number of elements in the range A to B. Okay. And actually, when we binary search, for example, when we binary search this guy, the runtime is not going to be log n, it's going to be log of the size of the segment. But it turns out there isn't really a way to simplify it to be smaller than log n. Because I guess, yeah, unfortunately, like log of A plus log of B is not equal to log of AB, A plus B. So we can't really like add up these logs to get like something better, to get like something smaller than log n. I mean log squared of n, but yeah. Okay, so here's the code. So the query function, what our query function used to do in normal segment trees is that it would return the tag of the intersection of the segment, of the current segment we are on and the query segment. Okay. But now instead it's going to return the number of elements in the intersection of the segment and the query range. So as usual, if the segment is outside of the query range, then we return 0 because there are no elements in the intersection that are in the range A to B. If the segment is completely inside the query range, then in this case, we have found one of the log n disjoint segments that partition the query range, okay? So in this case, we just need to binary search on the tag, on the sorted vector of all the elements inside our segment to count the number of elements in the range A to B. So I do like a binary search here and then another binary search here and I subtract them or something like that. Something along these lines will probably work. And then otherwise, then we just query the left and the right nodes and we add them together as usual. Notice that instead of using like f to combine these values, we just add them up. Okay. Yeah, we might need to add, yeah, definitely this line might be off by 1. I'm not really sure. I've never actually used this code before. But yeah, answer is maybe it's off by 1. But yeah, point of this is just to like, I guess, show that in this case, we need to do some kind of binary search to count the number of values in the segment. So this, I guess, important thing about this query function is that we are no longer using like f to combine stuff. Instead, we're just using addition. So this is the first example we've seen where our query function does not use the same function as our build function. Like it no longer uses f to combine values. We just use plus. Whereas in the build function, we would use f to combine stuff. And this is because instead of like finding the tag of the intersection, we want to just find the number of elements in the section. So we just add them up. Okay, that was probably unnecessarily confusing, but yeah, you can just imagine this as taking off the disjoint segments of these values here and just adding them up over the course of the recursion. Okay. Any questions on this problem? And the total runtime is log squared n per query, which is much better than, which is, I guess, better than our earlier solution using Mohs algorithm in most cases. So the total runtime is going to be q log squared of n. Mohs algorithm was n root n log n. I mean, yeah, okay, no. Yeah, it was n root n log n. And one interesting thing about Mohs algorithm is that it did not depend on the number of queries. I think as long as they're I'm not really sure why the runtime doesn't depend on the number of queries. for most algorithms, but I think as long as the number of queries as long as there are no duplicate queries, this will be the runtime. But that doesn't make any sense either. Okay, I'll think about this later in, I guess. But let's move on to another example of using segment trees with like more complicated data structures inside each node. So in this one, we have an array of n elements and we handle Q queries. Each query either asks us to change an element in the array or output whether X exists inside some subarray. So given a subarray and a value, output whether that value exists inside the subarray. So I guess compared to the previous problem, our queries are simpler. So instead of like counting them, our queries are seem easier at least because this query is just a special case of the previous one. We just want to find whether some value exists. We don't even want to find the number of times that value appears or anything like that. Just whether it exists or not. So this query is a special case of the previous one, but in exchange, we also need to be able to update our array. In the previous problem, we did not need to update our array. Okay. So maybe I'll give you guys a minute or so to think about what we might put inside inside the tag of each node that will help us answer our queries and also update efficiently. And I guess another note on the previous problem, the reason we can't update is because suppose we wanted to update an element in the array. This is talking about the previous problem. So to update an element of the array, we will need to update a bunch of like segments, one per level, right? Or something like this. Basically, every segment that contains the node that we updated will need to be changed. And it's not easy to like update a vector because we might need to remove an element like somewhere in the middle and then add another element somewhere in the middle because the vector should be sorted. So it doesn't seem like we can update the vectors efficiently. Okay, so that's why we didn't. But in the previous problem, this worked out okay because the problem didn't ask us to update. But yeah, in this one, we will need something different. Okay, so yeah, that pretty much looks exactly correct. So what we will do is for every node a node representing the segment L to R, its tag is going to be a multiset containing all the elements inside that subarray. Okay. So how can this help us answer queries? Well, as you mentioned, we can just, again, we do not want to merge stuff to find the tag of our query segment. Instead, we have our disjoint segments, and we want to check each one to see if it contains X. And then if any single one of them contains X, then we know that our entire query range contains X. Okay. So again, let's look at how to build stuff and check out the runtimes, I guess. So the easiest way is to just loop through all the elements in the segment and add them to the multiset. Our build function takes in the node and the segment that the node represents. So we can just loop through all the elements in the segment and insert them into the multiset, into the tag of our current node. Okay, and then we just recursively build the children if we're not at a leaf node right now. So what is the runtime of this? Okay, yeah, simply, it's just, yeah, it's nlog n. Actually, I'm not sure if it's nlog n. I think this is the same runtime as the vector one where we sorted stuff. Okay, I think we viewed that answer too fast, but yeah, let's, again, as usual, let's look at every level of our segment tree and see how much it costs. I think it will be nlog n per level. Yeah, the reason is because inserting into our multiset is nlog n time. So let's just be sure. So let's look at a segment. I mean, a level in our segment tree that has a bunch of nodes. Let's say there are X nodes. So on every single, for a single node, its segment size is going to be, okay, let's say M is the number of nodes. So the length of each segment is going to be N over M. So the cost to build its tag is going to be N over M insertions, and each insertion takes log N time. Log N. It's actually log N over M, but that's the same as log N in terms of big O. And then as usual, since there are M nodes, we multiply by M for this level, so the M goes away. And then we have another log N because there are log N levels in the segment tree. Okay. So total runtime is N log squared of N. There's also another way to build our segment tree, which is again to merge the tags of its children. So to merge two multisets, okay, we just create a new multiset, and then we go through every element in both multisets and insert them into our answer. So can anyone tell me what the runtime to build our entire segment tree would be using this function to combine tags? I think the insertions are going to be log n, always for multisets. Okay, it's still n log n squared. So again, let's look at a single node. Let's say we are on a level with m nodes, as usual. So take a look at any node on this level. It takes their n over its segment is n over m, right? And this is basically at this point it's basically the same as the previous one because we're just inserting a lot of stuff. We are inserting n over m nodes into its tag. So this is just going to take n over m log n time, and the rest is the same. Actually, this function is basically the same as the previous one because in the previous one we're just like inserting all the values necessary into its multiset, and in this one we're also doing the same thing. We're just inserting the necessary values into the multiset, so the runtime is exactly the same. So with multisets, unlike with sorted vectors, there's really nothing clever that we can do to make combining faster, I guess. So there's basically no reason to use this. But yeah. Okay. So the query, as we already said, we don't want to, as I already said, we don't want to merge stuff together to find the tag of the query range. Instead, we just look at the disjoint segments inside the query range and check if X is inside any one of them. So I guess we're kind of combining stuff using Boolean OR instead of plus, but yeah. So for example, if our query segment is like this, our query function is going to find the disjoint segments that partition this query range. And in each segment, in each of these disjoint segments, we can check if X appears in log n time. Because we have a multiset, we can just like find X. C++ has functions that do that for you, that check if X exists. So we check each one of these guys. If none of them contain X, then we know the entire query range does not contain X, so we can print out no. If at least one of these contain X, then we know the entire query range does contain X, so we can print out yes to answer our query. So runtime of this, as you already said, is log squared of n. And this is because there are log n disjoint segments, and inside each one, we need to do a binary search to find if X appears. Okay, so log n times log n, log squared of n, runtime per query. And to update, as usual, we have to, since we are updating a single element in the array, we have to update one node per level. So in general, remember in segment trees, when we update a single element, we have to update the node on every single level that contains that value that was changed, right? So for example, if we update this leaf over here, then we need to update like every node that contains that value. And to update a multiset, we just need to remove the element that was there before the update and add the element add the value that it was changed to. Okay. For example, suppose we want to update this node here. So the tag currently contains a multiset with all the elements inside that range, right? But we know that we like update some value here. We change it from like A to B, for example. So we just need to remove A from this multiset and add B to it. And this will update the tag to reflect the change to our array. Okay. And we need to do this for every single node, that for all of these nodes, and there's one per level. Okay. Does this make sense? So the runtime, it's going to be something like log n plus log of n over 2. So on the very top level, we have to update a multiset containing n nodes, and then we need to update a multiset containing n over 2 nodes. And then third level is n over 4 nodes, and so on. And this is just log squared of n. We can't really simplify this to be anything better. Because yeah, there are log n elements in the sum, right? And each one is at most log n. Each term in the sum is at most log n. So this is less than or equal to log squared of n. And in terms of big O, it doesn't get better than this. So this will be the runtime for updating our segment tree. So here's the full code for this. I think we already saw most of this. For build, we just loop through all of its elements and we insert them. For update, the parameters are I is a current node, SL and SR are the node, is the segment that node I represents, J is the index to be updated, and A and B are the previous value and new value respectively. And the reason we need to pass in the previous value is that we would know, is so that we can know what to remove from our multiset. Okay, so as usual, if the segment is outside of if the segment does not contain the update, then we can just return. Otherwise, the segment does contain the update. So we want to remove A from the multiset and insert B, and then we just update the children. Okay. In the query function, we are now like combining Boolean values for every. You can imagine for every disjoint segment, we either have true or false depending on if X is inside it or not. And then we want to combine these using Boolean OR. So if this, as usual, if the segment is outside of the query range, we return false. We know that X is definitely not inside the intersection of the segment and the query range. If it's inside, completely inside, then we just return true or false depending on whether the multiset contains X or not. So we do like the multiset dot find X, and we check if this is not equal to the end of the multiset. Otherwise, we query the two children and we just return the Boolean OR of those two values. Okay. So both query and updating takes log squared of n. So this is good. So the total runtime is q log squared of n. Any questions on this problem? Okay. So now that we have seen some examples of using more complicated data structures, we can finally move on to two-dimensional segment trees, which is just where the tag of each node is also a segment tree. Okay. So here's the motivating problem. So suppose we have a grid, n by n grid of integers. Here n is at most 400, but we're still going to try to solve it with 2D segment tree anyways, even though n is pretty small. And we want to handle Q queries, and each query either asks us to change a value of an element in the grid or output the maximum value in some rectangle, x1 to x2 and y1 to y2. And here I'm going to use x and y instead of using like standard row and column stuff for grids. I'm going to think about it as x and y coordinates, like on the coordinate plane. Okay. And we'll see why later why I like to think about it this way. But yeah. So just forget about rows and columns for now. Okay. So let's talk. So hopefully everyone remembers the problem. So let A be our grid, and we think about it in x and y. So A of x is a column at index x. We think of the grid as an array of columns. Okay. Maybe take a moment to read that again. So if you're actually doing this problem, you will want to build your array A, X, Y to like match the grid properly, I guess. And A, X, Y is just going to be the the value at coordinate x, at x value of x and y value of y. Okay, so we think of our grid as an array of columns. And of course, we are going to build a segment tree. So our overall segment tree, every node is going to represent some range of x values, okay? So let's look at what a node representing the segment x1 to x2 is going to contain as its tag. So suppose we have a node representing the segment x1 to y2. Consider an array B where B of y stores the maximum value for over all x from x1 to x2 of a x, y. Okay, and the tag of the node is a segment tree built in this array. So the slow example of what this math means. This value here is just the maximum of all values inside our grid that have y value equal to y and x value in the range x1 to y2. Okay. So for example, let's look at our grid here. Suppose this is our grid A. This is going to be our array B, as we will see. Suppose that the current node we are thinking about is representing the segment from index 1 to 3, x value 1 to 3. So it represents this portion, this array of 3 columns, okay? We're going to consider an array B, and B of y stores the B of y stores the maximum of all elements inside our grid with y value equal to y, okay? So B of 0 is going to store the maximum of these 3 elements. B of 1 is going to store the maximum of these 3 elements, and so on. B of 2 is going to store the maximum of these 3 elements, and so on. Yeah. To reiterate, basically, B of y just stores the maximum of all values in the grid inside the range x1 to y2. So in the grid represented by this segment that have y value, y coordinate equal to y. Okay. And our segment tree in the tag of this node is going to be a segment tree that is built on this B array. So currently the segment tree is going to hold the array 4753. So from index 0 to 3. Okay, this array here goes down to from bottom to up because the y value increases as we go up, right? So that's why the order is 4753. It goes this way. Okay, so just like maybe take a minute to look at this slide again and make sure you remember what's going on, like how we defined the tag of each node. So since we are working with like segment trees here, what's kind of going to happen is that suppose we want to update a element. Okay, so I guess one note about stuff I'm saying. So every single node has its own B array, but I'm not going to use like notation like B of I because that's kind of confusing. So every time I talk about the B array, I mean the B array of the node we're currently working with. Okay. So like let's look at an example of what might happen when we want to update an element in the grid. So suppose we want to change like this 2 to like 6 or something like that. So our B array will also need to change. So this will need to change to a 6 instead of a 3 because the maximum element in this row inside our range is now 6. Okay. So since our segment tree, the tag of this node is built on the B array, we need to update our tag using a segment tree update to reflect this change. Does that make sense? And note that this B array is not like something we will actually hold in memory or anything like that. We just keep in mind that our segment tree, the tag of this node represents this array. Okay. So every time we need to update a node, we need to think about how our B array will be affected by this update, and then we will need to update our segment tree, the segment tree tag of this node accordingly. Okay. And note that, I guess, when we update one element in the grid, at most one value in the B array changes, right? Only the value with with Y value equal to the Y value of the element updated will possibly change inside our B array. This means that at most we only need to update a single value inside the tag of this node, of node I. Okay. Any questions so far? Okay. I guess before we move on to like how to build our 2D segment tree and updating and stuff, I'll give you guys a few minutes to think about how we might be able to use these tags to answer a query. And remember that queries ask us for the maximum value in some rectangle from x1 to x2 and y1 to y2. And I guess this is pretty hard, but I just want everyone to spend some time like thinking about these tags, I guess, and try to get more familiar with the ideas so far. So just spend a few minutes thinking about stuff, I guess. I guess try to think about the log n disjoint segments that make up the range. So given a query of x1 to y2 and y1 to y2, think about the log n disjoint nodes that partition the range from x1 to y2. And what we can do is the tags of those nodes. I guess if anyone does think of it, it's pretty hard to type in chat too. So. Okay, so let's move on and talk about how to build our segment tree. And of course, we're gonna look at how to query data, but hopefully everyone had some time to get familiar with or think about what the B array means and like stuff like that. I don't know. But to build our array, we're just going to use the naive method, which is also the best method in this case. And we're just going to build node I, we're just going to build its B array and then construct a segment tree on it, okay? So to build our B array, what we're going to do is we're just going to initialize it, right? And then we're just going to loop through every distinct Y value or every row and just take the max. So sorry, this should be the maximum of B of Y and okay, so we're just going to loop through every Y value, and for every Y value, we will loop through all the values in the grid with on that Y coordinate and just take the maximum of all of those and put that value in B of Y. Okay. So in our grid from with x1 to x2, right? Basically, we just loop through. Yeah, we can just take the maximum of like y equals 0, the row y equals 0, and put that in B of 0, and so on. So pretty straightforward stuff. So now that we have our B array, we can just build our segment tree on it like this. So this is where you assume you have a segment tree class, right? Notice that our array, the type of every element inside our array is also a segment tree. So assume our segment tree class takes in an array and also the length of the array, and it constructs a segment tree based on that. Okay, so this line just builds a tag based on the B array. And then as usual, we build the children of our node if we are not at a leaf node. Okay, so can anyone tell me the runtime of this to build the entire segment tree? Remember, n is the dimensions of the grid. The grid is a n by n grid. Okay, yeah, it's n squared log n. First, what is the runtime of this line here? The runtime of this line is actually O of n. Because remember building a segment tree, or at least a basic segment tree, like maximum or addition of this line is not, this line, yeah, can anyone tell me what the runtime to build a segment tree is? Here we are building a segment tree with n using an array of size n. What is the runtime of that? This is just a basic segment tree, stuff we did in the very beginning. Actually, the time needed to build one of the basic segment trees is just O of n, right? And this is because the number of nodes is O of n. Right, remember a basic segment tree looks something like this. And so on. So on the first level, there'll be one node. Second level, there'll be two nodes. Third level, there'll be four nodes. And so on, all the way until the last level where there will be n nodes. What is the sum? The sum is just 2n, or approximately 2n, right? And in our basic segment tree, the runtime to construct each node is just constant time because we can just take the maximum of the values of its two children. So the time needed to build a segment tree, a basic segment tree like addition or maximum of a subarray is just linear. Okay. So it actually turns out we don't need to worry about the runtime of this line, because the runtime of this line is strictly more. What is the runtime of this line? It is going to be n times x2 minus x1, right? Because that is just the dimensions of the loop. We loop y goes from 0 to n, and x goes from x1 to x2. So that's the runtime of this. Okay, so to look at the entire runtime, again, let's look at it level per level, like each level of the segment tree. So suppose we have some arbitrary level of the segment tree, and this is our entire grid. It's definitely not a square right now, but assume it is, I guess. So to build this node, right, we need to loop through every element in the grid in the range x1 to x2, in the x range that this node represents. So we need to loop through this area. In the next node, we need to loop over this area and so on. And we can see that over all the nodes on this level, we loop through the entire grid once. Okay. So this loop over all the nodes on this level takes n squared time. N squared is just the number of elements in the entire grid. And we never need to worry about this line. It doesn't affect our runtime. So we don't need to worry about it. So every level of the segment tree takes n squared time. And since there are log n levels, the total runtime is n squared log n to build our segment tree. And this is pretty acceptable. Any questions on this? Okay, let's look at updating. This is the hard part. Okay, there's a lot of words here. Suppose we want to update g of xy to v. As usual, this will affect log n nodes. So we have our segment tree here. updating some column. So this leaf node kind of represents a column now. It's going to affect all the nodes that whose x range, whose segment contains x, right? So these segments that I just drew are just the x values that the nodes represent, the x range. So as usual, we need to update one tag per level, which is exactly the segments that contain x. And as usual, these values, these nodes form like a path down the segment tree. Okay. And also note that y does not affect which nodes are updated, and but instead it affects how we need to update the nodes, like how the tags of each of these nodes are updated, and we will see this soon. Okay, so what we will do is we will update these nodes from bottom up. So we will first update this one, then this one, then this one, and so on. Okay. This is kind of like in our original segment tree where we first update the leaf and then we merge tags together to update the parents or the ancestors as we go up the segment tree. Okay. So first we need to update the leaf. So how do we do this? So the leaf represents the range x to x, right? Because we are updating x, y. So the leaf is the only leaf that contains x, so the leaf is the range x to x. Okay. So let's look at the B array of this leaf. The leaf is just a single column, right? Represents a single column. And since the B array is just the maximum on each level, the B array is just equal to this column, right? Does that make sense? Since the leaf node is just represents a single column, right? A single x coordinate, its B array is exactly the same. So if we are changing like some index y to v, so suppose this is the index that is being changed, then we just need to update the segment tree at index y to the value v, because the B array is exactly the same as this column. Okay. Does this make sense? Maybe take like a few seconds to read this again. Okay, so we have so now we know how to update a leaf. Okay, let's see if we solve this. And now we are going to update the nodes from bottom up. So every time we are at some node to be updated, we know that both of its children are correctly updated to reflect the change that we wanted to make. Okay. Okay, so now suppose we want to update a node from x1 to x2, and we can assume that both of its children are updated. And this node represents some rectangle of our grid A from x1 to x2 and y from 0 to n. Okay? So it represents this array of columns from x1 to x2. And the B array, and also there's a B array of this, we have to think about the B array of this grid, right? Suppose this is the B array, it's pretty small. And each index of the B array contains the maximum value in that entire row inside the grid that our segment represents, okay? So now the main issue here is that we need to figure out how our B array changes. So let's just, since I'm running out of space, I'm just going to redraw the grid here. So suppose we are updating some value, for example, this one. The only B value that might change is this one, right? And the new value we need to update that the B array might contain in this spot is going to be the maximum of this entire row, right? So originally the B value is the maximum of this row before the change, and now we need the maximum in that row after the change. Okay. So how do we do this? It's pretty hard to find the new maximum without like sets and stuff, but we can actually do it using the fact that our children have been updated correctly. Okay. So let's look at the children of this node. The left child represents the left half of this grid, and the right child represents the right half of this grid. Okay. And also the tags of these children are the B arrays representing their respective grids. Consider these two values. So what I'm doing here is, this is the left child, and I query its segment tree from index y to y. So this is just getting me the element at index y. That's the circle that I just drew here, this one here. Okay. And same thing on the right. As the right child, which is this one, and I query that segment tree for index y to y, and this just gives me the value at index y, and that's this element here. Okay. Those two elements give me the maximum of these two like group rows respectively. Does that make sense? Maybe I'll change the color or something. Right? By the definition of the B array is just the maximum of the row in the corresponding grid. So when I take the maximum of these two values, I get the maximum of this area. Okay? I get the maximum of that area after the update, because we assume our children have already been updated. So then we can just update that, put this value into our B array here using a segment tree update. Okay. Any questions on this? Why does this happen? Okay, I don't know why that happens all the time, but yeah. Maybe take a moment to look at this again, look through this again, make sure you understand why this updates stuff correctly. Okay, let's reiterate this process one more time of updating some node. Okay. So we are updating this node here that represents this grid. We are updating index y to some value. So we want to find the new maximum of the row with y coordinate equal to y. We want to find this new maximum and put that into and update the tag with that value at index y. Okay. So to find the maximum of this row with the new update, we assume its two children are updated, and then we can find the maximum of the left half by querying b of y in the left child, and we can find the maximum of the right half by querying b of y of the right child. And when we take the maximum of those two values, we get the maximum of the entire row from x1 to x2, and then we can just update that into b of y for the current node. Okay, so that's how we update. This is definitely the hardest part of 2D segment trees, in my opinion. So should we solve this? Okay, so can someone tell me the runtime of our update function to update the entire segment tree? Okay, it is log squared of n because, as usual, there are log n nodes that need to be updated. So let's look at the amount of time needed to update a single node. Okay, so to update this node, first we need to look at the segment trees in its two children and query each one of them. This takes log n time. And then we need to do a segment tree update on the B array of our current node. And this also takes log n time. So it takes log n time to update a single node. And since there are log n nodes in total, it's log n squared. Okay, to update. Here's the code. It's pretty simple, despite the ideas are pretty complicated. So the update now takes in the node, the x1 and x2, the segment that our current node represents, and also x, y, and v, which means that we want to update the grid at the element in the grid at position x, y to the value v. Okay. So as usual, if the segment we're currently on, if the node we're currently on is outside of it does not contain x, right? Does not contain the position needed to be updated, we return. If we are at a leaf node, we do the special case we did earlier. We just need to update the tag at index y to v. Otherwise, we split it into two parts. We update both children. And then we need to update our current segment, assuming that our two children have been updated correctly. So here's the maximum value in row y. Okay, so again, we want our answer variable to store the maximum in the row at y coordinate y from x values x1 to x2. We want the maximum of this segment, and we want to put that in our answer variable. Okay, so to do that, we first find the maximum of the left half and the maximum of the right half. The maximum of the left half is just we query the left child for b of y. And the right half, the maximum of the right half, we just query the right child for b of y. And if we take the maximum of those two, we should get the maximum of the entire row. So we just update that into the segment tree of our current node at index y. Okay. So yeah, code is relatively simple. Okay. Now onto how to query our segment tree. First, we need to understand what what querying our segment tree of a node really represents. So suppose we have a node from x1 to x2. So this node represents the grid from x value x1 to y2 and y value from 0 to n. And we have this implicit B array from 0 to n, where B of y stores the maximum of the entire row at index y inside that grid. Okay? So suppose we query our B array for this range, for example. We take the maximum of all the values in here. Can anyone tell me what this value is in terms of our original grid? In terms of this grid here? What is the value of that, of the thing we just queried? Okay, it's actually the value that we just received from querying our B array from this range is actually the value in the entire grid in that range, in that y range. Okay. Why is that? It's because every B value in the B array is the maximum of the entire row. So we can imagine like the maximum of these entire rows going to the B array. So when we query for a range in the B array, we are querying a y value range, and each of those values in that range gives us the maximum of that entire row. So when we query our B array for a range, we are actually taking we are going to receive the maximum value in our original grid in that y range, but in the entire x range, from x1 to y2 of that grid, of that node's segment. Okay, does it make sense? So I wrote it down here. If a node represents a segment L to R, when we query the B array from y1 to y2, we get the maximum value in the rectangle L to R, y1 to y2. Okay. So now let's look at the queries, how to query. So suppose this is our entire grid, and we have some query rectangle like this. So this is x1, x2, y1 to y2. Sorry for the bad x. So as usual, we will partition the query range, which in this case is x1 to y2, into a bunch of disjoint segments. Suppose it looks something like this. Okay, and each of these disjoint segments represents a grid with x value in that range. Okay, so something like this. It turns out that what we should do to answer our query is to just query each of these segment trees for the range y1 to y2. Okay, so when we query the first one, it will give us the maximum value in this area, right? Because of what we said here. Right, when we query a segment of the B array, we actually get the maximum in the entire grid inside that Y range. Okay. And then when we query the next one, from Y1 to Y2, we get this area, and then this area, and so on, when we query each one. So when we add these values all up together, we actually get the answer for the entire query rectangle. for the entire rectangle that was queried. Does this make sense? So to reiterate, we have our rectangle to be queried. This is our query rectangle. Our segment tree is going to split this up into a bunch of disjoint segments. And by querying each of their segment trees, we add up all these pieces. We find the maximum of all these pieces. So we take the maximum of all these values, and we get the maximum of the entire query range, the query rectangle. Okay. So in reality, I only do in reality, the actual segments might look like this. I mean, these will be the actual grids, and I just drew the. Okay, that's pretty bad, but yeah. Any questions on querying the maximum of a rectangle using our two-dimensional segment tree? Okay. So here's the code for our query function. So there's a lot of parameters this time. So we have I is our current node. X1 and X2 is the X range that our node represents. And QX1, QX2, QY1, and QY2 are the bounds of the rectangle that we are querying for. Okay. And as usual, I guess the Y values of our queries do not affect which nodes we visit, but it affects like what we do with the nodes that we visit. Okay, so if our query range is outside of the segment, as usual, we return 0. If the segment is completely inside the query range, then we query the segment tree tag of our current node from index QY1 to QY2. Okay, that is giving us one of these things. So these are the actual grids. And when we find one that's completely inside, we will take the maximum of the entire grid, but we will take the maximum of all the values in the entire grid with Y value in the range QY1 to QY2. Okay, so that's what this query does. So otherwise, as usual, we query both children, and we just take the maximum of the two values on either side. Yeah, so code is relatively simple, but the ideas are pretty confusing, I guess. Okay, so this is it for 2D segment trees, I think. As usual, can someone tell me the runtime for this, for our query function? Okay, I mean, obviously it's going to be log squared of n because, as usual, yeah. So in a segment tree, the query that for search is going to visit log n nodes. And for each of these nodes, we will have to query. We might have to like do another segment tree query, which is going to take another log n. So again, log squared n. So both building and updating take log squared m time. Okay. Actually, I think it turns out for this problem, we don't even really need 2D segment tree. And this is because n is really small. So there are methods to like get past this, I guess, because n is so small. And the reason n is small here, like we can't make, like our query function will actually work even if n was like 100,000 or something like that, right? Because it's just log squared n. But the reason like the problem can't make n that big is because if n was like any bigger, then they couldn't really give us the input grid, right? The grid would be too big and they couldn't like give it to us. So here's a problem that actually requires 2D segment tree, I think. This is from IOI 2013 problem 6, so it should be pretty hard, but I think this is a pretty bad problem for the IOI. But in this one, we have a grid, and the grid is 10 to the 9th by 10 to the 9th. And the initial value of each cell is 0, so we want to handle Q queries of the following types. Change the value of a cell and output the greatest common divisor of a rectangle. Okay. So can someone tell me very generally how we can, I guess, modify our 2D segment tree to handle this question? Okay, yeah, so we will need to change basically all the maximums to GCDs. But also in this one, the grid is pretty big, right? We can't like, we can't really use arrays. Okay, I guess what I was looking for here is that instead of using segment trees, we use range trees. Yeah, we use dynamic trees, and we need to use dynamic trees both on the inside and the outside because both coordinates R and C can be up to 10 to the 9th. In general, depending on like your coordinates, you can make like a range. You can use like dynamic trees with segment trees on the inside or segment trees with range trees on the inside, but yeah, in this case, we will need to use a 2-dimensional range tree, and this is something you will need to implement for the homework problem this week. And I think that making the changes is probably a lot simpler than you might think if you understand how 2D segment tree works. But yeah, for this problem, you would just change the 2D segment tree we talked about for like the last hour to a 2D range tree instead, and you would just solve this problem immediately. So this is pretty bad for a IOI problem because you just plug in some data structures that everyone knows, but I think maybe at this time, maybe in 2013, people weren't familiar with this stuff. I don't know. But yeah. Okay, so last problem of today. So we are given an array A, and we want to handle Q queries. Each query is to change an element in the array, or also output the number of elements inside a range that are in the range A to B. Output the number of elements inside a subarray that are in the range A to B. And you might remember in the very beginning of today's class, we did this problem. We did a solution using Mo's algorithm, and we did another one with segment trees with vectors inside them. But in both of those versions, we could not handle updates to our array. But now we need to handle updates. So yeah. So think about how we can do this. Okay, good. So we can imagine, yeah, basically we imagine the points of we imagine the points in our array on a 2D plane. So we will have the point 0 and a of 0, and then 1, a of 1, and so on. All the, like in general, we have the point I, a of I, right? So on the coordinate plane, it might look something like we have 1 point per x value, and the y value of each of these points is just the value at that index in the array. Okay. And now when we want to let's build a 2D range tree on this one. Actually, we don't really need a 2D range tree. We can just have we can actually have the outer dimension can be a segment tree because n is only up to 10 to the fifth, and on the inside we have range trees. But yeah, a 2D range tree never hurts, so we can use a 2D range tree on this plane. Okay, and and we can say the value of each of these points is going to be 1. So now we want to find the number of elements in the subarray L to R that are in the range A to B. We just need to take the rectangle from L to R on the x coordinate on the x-axis and A to B on the y-axis. So we might have something like this where L to R is here and A to B is on the y-axis. And this will give us the number of points in the subarray from L to R that are in the range A to B. Does that make sense? And to change an element in the array, right? This is also pretty easy. All we need to do is we need to change the original point to have value 0, and we need to add a new point with value 1. So for example, if you wanted to change this point to something else, right? We will want to delete the point that's here. Inside our segment tree, this would mean changing the value of that point to 0 because in a 2D range tree, every point has some value. Most of them are just 0. So we would change the value of that point to 0, and whatever the new point is, we would change the value of that point to 1 instead. So now we can solve this problem using updates, like including updates using a 2D range tree, and both operations are log squared time, which is pretty strong because inside our original problem with vectors, I mean, in our solution at the beginning of class using vectors inside every node, our query runtime was also log squared of n. So now we can also handle updates without like making our query slower, which is pretty nice. Okay, one last point that I forgot to mention is the memory inside a 2D range tree. Okay. Remember, inside our like original dynamic tree, the memory was something like q log n or q log 10 to the 9th. This was the memory for our like one-dimensional like simple range tree because every time we want to do a query or some update or something like that, we visit at most log 10 to the 9th nodes in our range tree. Okay. So for example, if we want to update our range tree, we might like create we might have to visit some path down all the way to a leaf node. And then this will mean every node on this path will need to be created, and this will create at most log 10 to the 9th nodes. Okay. But inside a 2D range tree, again, on the outside, we visit all of the nodes on this path, right? For example, if we want to do an update, we visit all the nodes on this path. But inside of the nodes on this path, we also need to do a range tree update, right? And each range tree update inside here is going to create like another path in the other dimension, all the way to a leaf node. And all of these paths have length log n, log 10 to the 9th. So this path has log 10 to the 9th nodes, and each of these paths on the inside also has log 10 to the 9th nodes. So this is something you think about more as you work on the homework problem, but the memory should be something like q log squared 10 to the 9th. And a easier way to see this, I guess, is that since our tree is dynamic, the memory should never exceed the runtime, right? Because we are only using memory when we visit stuff. So the runtime should be at least the size of the memory. So since the runtime is q log squared 10 to the 9th, so the memory is also at most that much. Okay. Okay, so this is all I have for today. So this is it for data structures. This is it for today's class and also for our data structures unit in general. Next 2 lectures will be about trees, I think. Maybe like 2.5 lectures. I'm not sure yet. But yeah, this data structures part is definitely, I think, the most important part of USACO Platinum. And also, it's also one of the hardest. So, like, good job on everything. But yeah, see you guys next week, I guess.